Welcome to Advanced Embedded Systems, Lecture 32, where we will be talking about asynchronous design and the FPGA fabric. So make sure you do your time logs. Also, Lab 4 write-up is due today, so make sure you get that turned in and complete the lab if you have not done so already. Today we'll talk about asynchronous design in the FPGA fabric. First, we're going to start specifically talking about the Arctic 7 architecture and how things are placed on the board. Our FPGA consists of logic blocks, blocks of RAM, DSP blocks, and all other types of primitives that are interconnected through a routing network. We're going to spend most of our time talking about the logic blocks. But before we do, realize that modern reconfigurable logic, like FPGAs, exist because logic designs can be easily expressed in terms of these medium-scale logic blocks, similar to what we learned about in some of our design classes prior to this. We're taking these basic building blocks of shift registers, multiplexers, and things like that, and comparators, connecting them together to make a final design. This is actually, and I like this, this is what the output of Xilinx ISE looked like after synthesis of Lab 4 on our Spartan 6, which was what we used previous to the Arctic 7 Nexus videos. But the report looked a little different in ISE versus Vivado, but it shows you that all the primitives, the basic medium-scale logic blocks that are being used by that design, where we're using 13-bit adders, 16-bit adders, 8-bit adders, subtractors, things like that, and a multiplier, 16 by 16 multiplier. And we know what that's for Lab 4. That's to calculate our amplitude. So we're multiplying those 16-bit values and then taking that top 16 bits for our output. Again, the rest of it is registers, 21 of those, lots of different sizes, different comparators, multiplexers as well, and FSMs, finite state machines. So what does it show? It shows how our VHDL design is built of these basic building blocks. This is the lab report for Xilinx Vivado for my Lab 4 design, and I'll show you what that looks like. So, as you can see, here's the implementation utilization report, and I'll show those in the next few slides. That can be found in the reports section of your implementation design. So you have your synthesis reports, maybe take a look at those sometimes. It doesn't quite show the same details as ISE used to, but I'm looking at this report here. I also looked at the synthesis report as well. But shows the device, Lab 4 is our design, and it was placed. This is a summary of everything in the report. It's going to talk about slice logic, memory, how it uses everything on the board. It doesn't quite show the same things as it used to. It does show the utilization of lookup tables, LUTs, slice LUTs, which we're going to learn about. LUTs is logic and memory, flip-flops, registers, not as much as important. How many slicels and slice M's we're using. We're going to talk about that in just a little bit. Slice registers and so on. Block RAM, RAM 18s. We're using 2 of those, which we're initializing the 2 different lookup tables in there. and DSP modules. Some other stuff in there, you can take a look. Input-output buffers, so those are input-output, IOBs. Flip-flops, carry logic, and clocks. But ultimately today we're going to talk about the logic blocks and how those are put together. So all this is derived from the Xilinx Configurable Logic Block User Guide, which is linkable from the notes page as well. This is the user guide. And this is what we're going to be going over next few slides. This is a configurable logic block. Each block is implementing VHDL, but implemented on the FPGA fabric. This is what we've been using to create these designs. Each CLB is laid out in an array, basically a switch matrix on the FPGA fabric, and everything is interconnected to these configurable logic blocks. Each block contains two slices, slice 1 and slice 2. You can have carry ins and carry outs in each of those slices as well. We're going to talk more about that in just a second. This is out of the Arctic 7. So this is how each CLB is laid out. If we had, and this is right out of the user guide as well, this is the row and column relationship of each CLB, how they're put together on the grid. So let's look at each of those slices. That's the bottom left corner of the die. Let's look at those slices. On our Arctic 7 board, we have the Arctic 7 chip, the 7A200T, and if you look in here for A7A200T, it shows how many resources we have. We have 33,000 slices, slicels and slicems. There are different types of slices, and we're going to talk about the difference between those. How many lookup tables, 6 input LUTs, distributive RAM, and shift registers and flip-flops. Lots of resources available to us. Right, so 16 825 CLBs. There's 6 input LUTs, 8 flip-flops for each slice. And that corresponds to the total 134,600 lookup tables. There are 3 types of slices, slicems, slicels, and slice X, which we'll talk about. We're going to take a look mostly at the slicem, just because they're a little, has the most features, so we're going to look at that one. The other ones are similar, they just don't have quite as many features as the slice M's. So let's look at that slice M. In this diagram, you can see 3 major subsystems, and I mean, it looks like a lot at the beginning until you start looking at the individual parts. So the first one, for 6 input LUTs, we have a lookup table here, 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 and here. So 4 lookup tables. Notice they're labeled A, B, C, and D, starting from the bottom. There are 8 flip-flops. 1, 2, 3, 4, 5, 6, 7, 8. And then some fast carry logic in here, all these gates and muxes and whatnot, from carry in to carry out, and we'll talk about each of those subsystems shortly and how they're all put together. So in one of these sliceums, each slice in a sliceum there are 64 by 1 RAMs, which are essentially these lookup tables that are set up for lookup tables, 6 input LUTs. So it's 64 bits. How many bits do you need to address each of these 64 rows, 64 by 1 RAMs? So it's a lookup table. You need 6 bits of address to be able to address each of those values. So we have address lines coming in to address each of those rows in the lookup table to be able to actually implement different functions. So again, it's if you as an example, we'll try to derive the truth table for a sum and carry and show how each of them can be inserted into one of these lookup tables, these 64-row lookup tables. It'll be important to point out that sum is going to be equal to A exclusive OR with B exclusive OR with C, and that is for an actual full adder. You have A, B, and C, and you're going to exclusive OR each of those, and carry out can be represented by A exclusive OR with B and C in, or A and B. So that's just some of those basic logic functions that we learned about before. So again, you got your 4 lookup tables, 1, 2, 3, 4, or A, B, C, D. You also have 8 flip-flops in each logic slice. We're going to answer the following questions. Where does the data input come from for each of those 8 flip-flops? So we have our 8 flip-flops, and you notice if you just trace it back, output 6 goes into the MUX, and we also have BX going into that MUX as a data input. So you have a D input and then a Q output for each of these flip-flops. The ones on the right, so that's output 5 and output 5, as well as AX, and then output 5 of the B lookup table, and then BX, all those inputs. Then you also have, for these, those D inputs come from these large MUXes that take many different inputs. On figure 7, page 14 of that manual, you can also see a little close-up of those inputs, typically LUT D, A through D, output 5. There's actually a multiplexer, so you can select 2 different inputs. But output 5 would be the input, and this one inputs these on the registers on the right. So you have, these are flip-flops plus latches. So it's dual purpose depending on what the inputs are and how it's clocked. Then these on the left are registers only, and where those inputs come from. How are the signals clocked, or how the slice is clocked? You can see there's a clock line coming in. There's 2 different polarities for that. So you can have negative or positive polarity, but it goes to every clock input to each of, well, it doesn't show the connection here, but it does connect to these other registers as well. How are the slices initialized? They're initialized using this SR input, that is a synchronous reset. And each of them is connected to this SR line coming in. So we have a synchronous reset on every flip-flop. So that supports a registered read from a distributed RAM or additional pipeline stage in the shift register while allowing an initial initialization value. Then where are the outputs sent? Again, if you look at this, it goes to DQ, AQ, BQ, CQ, DQ. Out of each of those outputs, it's going to go to the output mux from that slice. So the last part of those is a fast carry logic. Consider how you set up a 4-bit adder. So if you have a 4-bit adder with inputs A3 down to 0 and B input B3 down to 0 and a carry in. So you have 4 inputs for each of the A and B and then a carry out. Each slice of the adder can generate a carry bit or a propagate bit. Its carry in goes to the carry out. So we have carry in coming in for each slice in the bottom. Lots of hardware in there for each of those bits. And lookup tables, and then we have a carry out going through to the top. Propagate is essentially when we're trying to propagate a 1 carry through the bit slice through adding of the A and the B inputs and getting that carry out to propagate to that next higher bit from bit 0 to bit 1 and 2 and then to 3. A generate is equal to 1 when the inputs of the bit slice are such that a carry will be generated, right? So if you have a 1 coming on A and a 1 coming in on B, it will generate an output carry. But if I have a 0 here and then a carry in, it's going to propagate that carry through, right? So carry out is essentially generate or propagate and carry in, right? And that's the basic function of generate and propagate for those carries. So as we have these 4 inputs, 4-bit inputs, A and B, we can add them and propagate through a carry out. How are all these slices interconnected though? They're interconnected. This figure it's from the Spartan 6 FPGA user guide, page 37, figure 29, linked from here. It's a little better than what they had in the newer version, but it just basically shows each, the switch matrix with the configurable logic blocks, similar to the images we saw before, but everything is connected on this grid array and everything's interconnected via these switch matrices so that they can actually tie into each of those CLBs and tie in those values. Another thing we have on our FPGA logic is DSP, digital signal processing slices, available to us. These, there's 700 DSP 48 E1 slices. Each slice contains a pre-adder, 25 by 18 multiplier, and an adder and an accumulator. Here is what that looks like. You have your A and B in, P in, and you have your PC out and A out. You got lots of registers, you got that 25 by 18 multiplier, you got adders, and then depending on the ALU mode, you can do lots of other functions. with that as well, based on those inputs. Lots of different functionality. And that's all in the user's guide as well. There's a complete user's guide on the Xilinx 7 series DSP slices and how we can use those. So that concludes today's lecture. Mostly in class today, we are going to be talking about what's coming up on the horizon, which is the exam on Monday and Lab 4 being completed and getting that signed off. Make sure everything's good to go for the write-up. And then the rest of the semester, we're essentially working on your individual projects, which the final project plan, more detailed than the proposal, is due next Wednesday by close of business. It's a little more detailed than the project. It's going to detail your threshold and your objectives of what you want to do. A little more details, since you've done a little bit of research into your project, on those interconnects and how everything's going to be set up.